Hello, my name is John Watrous, and I hope that you're enjoying the 2025 Qiskit Global Summer School so far. This is the first part of a two-part lecture on foundational quantum algorithms. This first part is on Deutsch's and Grover's algorithms, which are comparatively simple, but are nevertheless fundamental examples of quantum algorithms. The second part of the lecture will be on phase estimation and Shor's algorithm, and that'll be coming up in the next video. The essential idea for both parts is to consider quantum computing from a theoretical perspective and to investigate what we can hope to do with quantum computers and what sorts of advantages a quantum computer might potentially have over classical computers for solving computational problems. Before I get going, let me mention that the material that I'm going to be covering in these lectures is also covered in the series called Understanding Quantum Information and Computation that we recently completed here at IBM. That series has 16 lessons in total, including 4 lessons on the basics of quantum information, which you may find to be helpful if you're new to quantum computing, as well as 4 lessons on quantum algorithms. And it also includes a written text that goes along with the videos, so there's a lot more detail in that series and more background coverage as well, in case you are interested. You can find the Understanding Quantum Information and Computation series on IBM Quantum Learning and on the Qiskit YouTube channel. Let's begin with a very simple way of thinking about computation abstractly. We're going to switch things up in just a moment, but this is a good place to start because it's both standard and intuitive. Here's a picture that represents a computation in extremely simple and basic terms. We have an input, which usually takes the form of a binary string, although we could use different symbols if we wanted to. The input is provided to a computation, which is represented by a blue rectangle in this picture, and the result of the computation is that some output is produced, and again, that's most typically a binary string. Of course, this picture is not at all specific about how the computation itself works. We can formulate different computational models to do that, such as Turing machines and Boolean circuits, or quantum circuits if we're thinking about quantum computations. To be clear, this picture doesn't represent the fact that many of the computers we use every day are constantly receiving input and producing output, essentially interacting with both us and with other computers. But we're not trying to represent those sorts of interactions here. This is about modeling isolated computational tasks. The key point here is that the entire input is provided to this computation, and nothing about the input is hidden from it. There's another model of computation known as the query model of computation that works differently. And this is the model that we're going to start with. Just to set the stage, let me say right here at the start that this model is not intended to be a practical model or a realistic way of describing computations. Instead, it's better thought about as a rigid framework for studying algorithms. It can be connected back to the more standard model of computation we saw just a moment ago, though, and we'll discuss that more later on. In the query model, the input is made available not as a string, but rather in the form of a function, which the computation can access by making queries, or in other words, by evaluating the function on different inputs. Here you can see that represented in the form of a picture. Similar to what we had before, the computation is represented by a blue rectangle, but instead of receiving an input directly in the form of a string of bits, the computation accesses the input by effectively asking questions about it and receiving answers. We sometimes use the terms oracle and black box to refer to the mechanism that provides the input, and these are reasonable names for conveying the basic idea. In ancient Greece, you could go to an oracle and ask a question that was important to you, and the oracle would answer that specific question, but of course, she wouldn't tell you everything she knew. Along similar lines, when we think about a black box, we have in mind some sort of process or system where we can choose what goes in and we can see what comes out, but we don't have any understanding of its inner workings. And that's the case here. The input to the problem takes the form of a function, and all we can do is to evaluate that function, but otherwise we don't have any knowledge or understanding of how it works. Throughout the talk, we'll reserve the letter f for the function that represents the input, and we'll make the assumption that it always takes the form that's shown here. Sigma denotes the binary alphabet, or in other words, the symbols 0 and 1. So f is a function from strings of bits to strings of bits. And specifically, we'll assume that the input f is a string of bits having length n, and the output is a string of bits having length m, where n and m are positive integers. When we say that a computation makes a query, what we mean is that the function f is evaluated once. So some string x of length n is selected by the computation, and the string f of x is then made available to it by the oracle or the black box. And finally, the very simple way that we'll measure the computational cost of a query algorithm is to count how many queries it makes. That's definitely a simplification. Ultimately, we're really interested in how long computations take and what resources are required. But when we study the query model, we generally keep things simple and just count queries. Here are two very quick but important points about this. First, when we do this, meaning measuring efficiency by counting queries, we're completely ignoring whatever cost or difficulty is associated with implementing the oracle. This doesn't mean that implementing the oracle is somehow trivial or unimportant or not necessary for actually performing computations, but rather we're simply focusing on the task of solving query problems given that the oracle is already available. One way to think about this is that the oracle represents the problem input, and our focus is on solving problems given the input rather than preparing the input. However, we can connect the query model back to the standard computational model that I mentioned at the start of the talk. In particular, it is sometimes possible to solve a standard computational problem where we're given an input as a string of bits in the typical way by making use of a query algorithm, but where the implementation of the oracle is considered to be a part of the computation. And in that case, we must naturally consider the cost of doing that when analyzing the algorithm. Now let's take a look at a few examples of query problems, meaning computational problems in the query model. At this point, by the way, I'm just going to describe the problems themselves, and I won't say anything just yet about how to actually solve them. The first problem is the OR problem. In this case, the input is a function from n bits to just 1 bit, so m is equal to 1 for this problem. And the required output for this problem is either 1 or 0. If there's some n-bit string x for which f of x equals 1, then the correct answer is 1. And otherwise, if f of x is always 0 for every x, then the correct answer is 0. So, if we think about the function f as providing us with random access to 2 to the n bits, 1 for each n-bit string x, then what the problem is asking for is the OR of those bits, and that's why it's called the OR problem. Another example is the parity problem, which is similar to the OR problem, except that it asks for the parity, or in other words, the exclusive OR, of all of the single-bit output values of the function. Another way to say that is that the correct answer is 0 if the number of n-bit strings x for which f of x is equal to 1 is even, and the correct answer is 1 if that number is odd. An example of a problem where m is not necessarily equal to 1 is the minimum problem. So here the function f takes the usual form, and there are no restrictions on n and m, and the correct answer is whatever output value of the function comes first in the standard dictionary ordering of binary strings. Alternatively, if we think about strings of length m as representing non-negative integers written in binary, then the correct answer is the smallest possible or minimum value that comes out of this function. Sometimes we also consider problems where we have a promise on the input function, or in other words, some guarantee on it, and we don't worry about functions that don't satisfy that promise. In essence, functions that don't satisfy the promise are considered as don't care inputs, and we're not responsible for what happens on those inputs. Here's an example of a query problem with a promise called unique search. It's related to the OR problem, but it's different. The input function has the same form as for the OR problem, which is that it takes n-bit strings to bits, This time, though, we're promised that there's exactly one string z that causes f to evaluate to 1, with f of x being 0 for every string x besides z. And the correct output is this unique string z. Of course, there are choices for the function f that don't satisfy this condition, but we don't place any requirements at all on algorithms for this problem when they're given such functions as input. We only care about the functions that do satisfy the promise. We can formalize the notion of a query in different ways, depending on what specific computational model we're working with. For circuit models, we define special types of gates called query gates, and that's how queries are formally represented. For Boolean circuits, there's a very simple way to do this, which is simply to imagine that we have query gates that evaluate the input function directly, like is shown here on the slide. The idea is that we can use these query gates to build circuits that solve whatever problem we're looking at, and in order to work correctly, the circuits have to give the right answer for whatever input function f is given, assuming it meets the promise in the case of a promise problem. Here's a simple example of a Boolean circuit that solves the parity problem when n is equal to 1. So the input function f is from 1 bit to 1 bit in this case. What the circuit does is to evaluate the function f on the inputs 0 and 1 using the two query gates that are shown on the left, and then it plugs the two output values it gets from the query gates into a Boolean circuit that computes the exclusive OR, which is the same thing as the parity. Just to be sure it's clear, the two input values on the left, 0 and 1, are inputs to the circuit, but they're not inputs to this problem, meaning the parity problem. When we're working in the query model, the input to the problem is the function f. So you should think about these two inputs into this circuit as being hard-coded values that never change. Basically, they're part of the algorithm. We want to compute the XOR of f0 and f1, so we initialize these two input wires in this way to make it work. We've used two query gates, so the algorithm represented by this Boolean circuit makes two queries. And if we think about the parity problem for a moment, for a function from 1 bit to 1 bit, we see that it's absolutely necessary for any Boolean circuit that solves this problem to make at least two queries. If you only make one query so that you know only one of the output values of f and not the other, you don't actually have any information at all about the parity, because the other output value could equally well be 0 or 1, leading to either of the two possible solutions to the problem. So, in terms of the number of queries that it makes, this Boolean circuit is as good as you can do for the parity problem when n is equal to 1. Now let's turn our attention to quantum circuits. For quantum circuits, we're going to change our definition of query gates to make them unitary. We want to be able to make queries within quantum circuits and for them to operate linearly on quantum states, so we can effectively make queries in superposition, so that's the reason for doing this. Specifically, the definition is as follows. Given any function of the same form as before, meaning that it maps n-bit strings to m-bit strings, the query gate UF acts on n plus m qubits, and is defined by the action described here on standard basis states. We'll see a figure representing this definition in just a moment, but first let me make clear the notation that's being used here, and that is that whenever we use the symbol for the XOR as an operation between two strings of the same length, we're referring to the bitwise exclusive OR, and here on the slide is a simple example. In the definition, we have that both y and f of x are strings of length m, so y XOR f of x is the string we get by XORing those two strings together 1 bit at a time. And here's a diagram explaining how these gates work. The top n qubits correspond to the argument of the function, and when they start out in a standard basis state, Kx in this diagram, that standard basis state goes through unchanged and gets echoed as part of the output. The bottom m qubits correspond to the output of the function f, and when they start out in any standard basis state, ket y in this diagram, what happens is that the output of the function f of x gets XORed onto the string y. This is what happens for standard basis states, and if we want to know what happens in general for other quantum states, we use linearity. The reason that we define query gates like this, where we echo the input and we use the bitwise exclusive OR for the output, is that these gates are always unitary for any choice of the function f. This is, in fact, a deterministic operation, and if we were to express it as a matrix for any choice of a function f, we'd get a permutation matrix, meaning one with a single 1 in each row and in each column, and all other entries being equal to 0. And permutation matrices are always unitary. In fact, for this operation, we'll get that the operation is its own inverse, so UF dagger is equal to UF. By the way, if all we want to do with these gates is to evaluate f of x for some string x, then that's easy. We can just set y to be the L0 string, so that when we take the bitwise exclusive OR, we end up with just f of x. Here, by the way, you can see the notation that's used to denote the L0 string. It looks like 0 to the power m, but that's not what it means. It just means the string of zeros having length equal to m. Once again, when we're working with the query model, we aren't worrying about how to implement these query gates. That's the same issue we had with query gates for Boolean circuits. However, if we do know how to implement a particular function f using a Boolean circuit, then it is possible to translate that implementation pretty directly into a quantum circuit implementation of UF. And you can take that fact as at least a partial justification for why this is a reasonable definition of a query gate for the quantum circuit model. Next, we'll discuss Deutsch's algorithm, which is a very simple quantum query algorithm, but it really is a gem. This algorithm comes from a 1985 paper written by David Deutsch, who was one of the very first people to work on the theoretical foundations of quantum computing. The algorithm itself represents a very small part of Deutsch's 1985 paper, and in fact, the algorithm that we now call Deutsch's algorithm is actually an improved version of the algorithm that Deutsch described. It provides a very modest example of how quantum computers can offer computational advantages, but you have to start somewhere, and it really was an important spark that got things started. Deutsch's algorithm solves a query problem that's often called Deutsch's problem in the context of quantum computing, but in fact, it's actually just a parity problem for functions from 1 bit to 1 bit, which we've already talked about. In greater detail, there are 4 functions from 1 bit to 1 bit, and they're described here on the slide by their tables of values. The first and last of these functions are constant, while the middle 2 are balanced, in the sense that the 2 possible output values both appear once. For the 2 constant functions, we see that the parity, or in other words, the exclusive OR of the 2 outputs, is 0, and for the 2 balanced functions, the parity of the outputs is 1. So, an equivalent way to describe the parity problem in this particular case, where the function f takes a single bit as input, or in other words, Deutsch's problem, is shown here. The input is a function f from 1 bit to 1 bit. The output is 0 if f is constant, and 1 if f is balanced. As I've already mentioned, every classical query algorithm that solves this problem must make at least 2 queries to f. If you learn just one of the 2 output values of f, you still have no information at all about the parity of the 2 outputs. And this, by the way, is true even for classical algorithms that make use of randomness. Randomness can sometimes be very useful for solving query problems, but it doesn't help here. So, our algorithm from before is optimal among classical query algorithms for Deutsch's problem. Now we'll take a look at Deutsch's algorithm, which is a quantum query algorithm that solves Deutsch's problem using a single query. And here is the algorithm described as a quantum circuit. We have 2 qubits, with the top one initialized to ket 0 and the bottom one initialized to ket 1, and we'll see why we initialize these qubits like this shortly. We perform Hadamard gates on the 2 qubits, feed them into the query gate, perform another Hadamard gate on the top qubit, and then measure it. And the claim is that the measurement outcome gives us, with certainty, the correct answer to the problem. So let's analyze the circuit one step at a time to see exactly how it works. The state of the 2 qubits after the first layer of Hadamard gates is the tensor product of the minus and plus states. The Hadamard on top maps the 0 state to a plus state, and the Hadamard on the bottom maps the 1 state to a minus state. Please note, by the way, that the top qubit is on the right, and the bottom qubit is on the left, because that's the convention that Qiskit uses for ordering qubits, so this is the state that we get. We're going to expand this state halfway, basically, like is shown here. The reason for doing that may not be clear at this point, but it will be convenient in just a moment. Next, let's think about the state of the two qubits after the query gate is performed. The way the query gate works is that it computes f on the standard basis state of the top qubit and XORs the value onto the bottom qubit, and here we can see the result of doing that. For the first term, the standard basis state of the top qubit is 0, so f of 0 gets XORed onto the bottom qubit, and that works by linearity, and it's similar for the second term, except that the standard basis state for the top qubit is 1, so we XOR f of 1 onto the bottom qubit. And at this point, we can simplify this expression by observing the formula that's shown on the bottom of the slide, and that works when b is either 0 or 1, and we can simply check this for the two values separately. If b is equal to 0, then XORing with b does nothing, and negative 1 to the power 0 is 1, so the two sides are equal. And if b is equal to 1, then we get ket 1 minus ket 0 when we take the exclusive OR, which is negative 1 times ket 0 minus ket 1. And if we use that formula to simplify our state, where we take b is equal to f of 0 on the left and b equals f of 1 on the right, we get the expression that's shown here on the slide. So, when we compare the two quantum state vectors, pi1 and pi2, we see that what the UF gate does is effectively to put one of the two values, f of 0 or f of 1, into the exponent of negative 1, or in other words, into the phase of each term. This is, in fact, the reason for initializing the bottom qubit to 1 and performing a Hadamard gate on it, to create the minus state which allows this to happen. It's called the phase kickback phenomenon, and we'll come back to it in a few moments to have another look at it. We can now simplify by pulling the minus state back outside to get the expression that's shown here. So let's clean this up a bit so that we have a little bit more room. What we can do now is to pull a factor of negative 1 raised to the power of f of 0 outside to get this expression of the state. You'll notice here that we have the exclusive OR of f of 0 and f of 1 in the exponent of negative 1, which you might have expected to be f of 1 minus f of 0 instead, because we pulled out a factor of negative 1 to the power f of 0. But we get the same value if we take the XOR, because these are bits, and the only thing that matters when we have an integer in the exponent of negative 1 is whether that integer is even or odd. Another way to express this state is like we have here, where we're explicitly considering the two possible cases for the XOR, and that's a convenient way to express the state as we consider the action of the final Hadamard gate together with the measurement. When we perform the last Hadamard gate on the top qubit, the plus state is transformed into a 0 state, and the minus state is transformed into a 1 state, and we can write this more succinctly as we have here. And finally, when the measurement is performed, the result we obtain is therefore the XOR of f of 0 and f of 1, which is the value that we're looking for. And that's how Deutsch's algorithm works. If we ask ourselves, what is it that makes this work, allowing us to compute the parity of 2 bits with a single query rather than 2 queries, a reasonable answer is that it's interference. We're effectively computing f of 0 and f of 1 at the same time, because we first performed the Hadamard gate on the top qubit to put the input of f into a superposition of 0 and 1, and by means of the phase kickback phenomenon, together with the final Hadamard gate, we're essentially creating constructive interference for the correct answer and destructive interference for the wrong answer, so we don't see the wrong answer, we see the correct answer. Now let me say a little bit more about the phase kickback phenomenon, just to see it from a slightly different angle. First, let's observe this very simple formula where b and c are arbitrary binary values. In short, XORing a bit b by the value 1 is the same thing as performing a NOT or an X operation on b, and of course, XORing a bit b by the value 0 doesn't do anything to it, which is the same thing as performing the identity operation on it, and we can express the identity operation as x to the power 0. So, if we perform a UF gate on 2 qubits in the standard basis state ket B tensor ket A, we obtain this outcome just by the definition of the UF gate, And using the formula, we can alternatively write that state like is shown here. This formula works for all choices of B, so by linearity, it works for an arbitrary state psi in place of ket B. And in particular, if we want, we can choose psi to be the minus state. And now here's the key to why the phase kickback phenomenon happens. It's because the x operation applied to the minus state gives us -1 times the minus state. In mathematical terms, we say that the minus state is an eigenvector of the x operation with eigenvalue equal to -1. Eigenvectors and eigenvalues are critically important in linear algebra as well as in quantum information, but for right now, all we need is this very simple formula. And using it, we can simplify our state vector. And that right here is essentially the phase kickback written as a formula. It works because the minus state is an eigenvector of the not operation having eigenvalue -1. We'll generalize this in a pretty major way in the second part of the lecture, by the way, when we turn to the phase estimation procedure, which is what drives Shor's factoring algorithm. We can see this formula in action in the analysis of Deutsch's algorithm as follows. Prior to the query gate, our state is the tensor product of the minus and plus states. We then apply the query gate, and expanding out the plus state gives us this. We now apply the phase kickback phenomenon to get this expression, and then the analysis carries on like it did before. It's the same analysis as before, but here we're just focusing in on the phase kickback phenomenon so we can recognize it and also be ready for it when it comes up again. Next, we'll discuss Grover's algorithm, which is a quantum algorithm for so-called unstructured search. Intuitively speaking, we can think about unstructured search as searching through a collection of items that isn't sorted and hasn't been ordered in a useful way. We can formalize this problem as a query problem in the following way. The input takes the form of a function f that maps binary strings of some length n to the binary alphabet. As a query problem, access to this function is provided by an oracle, but it does make sense to imagine that this is a function that we can efficiently compute, which allows us to actually implement this oracle with a circuit. Our goal is to find a solution, by which we mean a binary string of length n that causes f to evaluate to 1. A little bit more formally, the problem can be stated as a query problem like is shown here. So, conceptually speaking, the input to the problem is this function f, and we're looking for any solution if there is one. And if there isn't a solution, meaning that f turns out to be the all-zero function, then the correct output is to report that there are no solutions. This is an unstructured search problem in the sense that there's nothing special about f that makes it easy. It's not like we're searching through data that's already been ordered or that's been loaded into a data structure of some sort that facilitates searching, and there's no promise on this function that might help us. One way to think about it is that it's like searching for a particular phone number in a phone book, as opposed to searching for a name in an alphabetized list. In practical terms, it's not really about searching through data, which we tend to organize and store in a manner that makes searching easy. It's more representative of searching for a solution to a complicated equation, for instance, or perhaps searching for the combination that opens a lock. Now let's think about algorithms for solving this unstructured search problem, focusing on the query model. If instead we had a Boolean circuit for our function rather than a black box, then we could still run a query algorithm on it, but we definitely can't rule out the possibility that some new algorithm that isn't based on making queries offers a better solution. First, here's just a little bit of notation. The total number of input strings to the function f is 2 to the little n, where little n is the length of the input strings to f, and hereafter I'm going to let big N be this number, 2 to the little n. Now, of course, we can solve the search problem classically by simply iterating through all of the possible n-bit strings in whatever order we choose, evaluating f on each of them. If we find a solution at any point, we can stop, but in the worst case, we'll end up having to evaluate f on every single input string. So this requires n, meaning capital N, queries. And this is, in fact, the best that we can do with a deterministic algorithm. And again, this is in the context of the query model. If you've queried the function on every input string except for one, and f has taken the value 0 on all of them, how can we be sure that the last string isn't a solution or is a solution? And the answer is that you can't, so you do in fact need to query that last string, which means n queries in the worst case. We could also use randomness, and that can offer some very minor improvements, such as a reduction in the expected number of queries that you need in order to find a solution when one exists. Or you could effectively trade correctness probability for a reduction in queries. But however you slice it, we will need a number of queries that's linear in capital N. So classically speaking, we need a number of queries that's linear in N. Grover's algorithm is a quantum algorithm for search that does better. It requires just big O of the square root of n queries. Those queries happen in superposition, so this isn't magic, but it is a significant improvement over what's possible classically, and this is what's meant when we refer to a quadratic advantage. Can this quadratic advantage of quantum over classical be turned into an actual advantage in a practical sense? Probably not anytime soon, but in the distant future, who knows? But even if Grover's algorithm doesn't ever lead to a practical advantage for searching, it is nevertheless an important part of the foundation of quantum algorithms that's well worth understanding. Before we move on to Grover's algorithm itself, we need to talk briefly about so-called phase query gates. Many quantum algorithms in the query model are naturally expressed using phase query gates, and we'll see that Grover's algorithm is a specific example. For a function f of the form that we've been talking about, the query gate UF is defined on standard basis states as is shown on the slide, and for superpositions of standard basis states, the action is determined by linearity. The phase query gate for f, in contrast, operates like this. In particular, this gate operates on little n qubits as opposed to little n plus 1 qubits, and it basically just kicks the function value into the phase rather than XORing the output value to an additional qubit like we have for UF. So if we think about what happens when we use the phase kickback phenomenon on a UF gate, we're basically just implementing a ZF gate. We need a minus state, and it costs one evaluation of UF, but we do get the minus state back, and we can use it for the next one if we want to, or we could just throw it away. So that's what a phase query gate is. Now, if you're just given a gate for ZF, and this is the only way that you can access the function f, then you actually can't recover a UF gate. But if you have a controlled version of a ZF gate, then you can build a UF gate, and I'll leave that one for you as an exercise. In addition to the phase query gate for the function f, we're also going to need a phase query gate for the n-bit OR function, and explicitly the way that Z-OR works for standard basis states is shown on the slide. This gate doesn't have any dependence on the function f, so it doesn't require any queries. It isn't too difficult to build a quantum circuit that implements this operation using standard methods, but I won't explain that in this talk. And now that we have these gates, we're ready to move on to Grover's algorithm. Let's begin with a description of Grover's algorithm. We start by initializing little n qubits each to the plus state, or in other words, we put these qubits into an equal superposition of all binary strings of length n. What we're going to do is effectively to steer the state of these qubits toward a solution. So it's intuitive that we start out in this state because we don't know anything about f at this point. Every string is equally likely to be a solution, and that's reflected by the fact that these qubits are in an equal superposition of all strings. And then we iterate. We repeatedly apply the Grover operation, which is really the heart of the algorithm, and I'll describe it in just a moment. We apply this operation a total of t times, where t is some non-negative integer, but this number isn't actually specified by the algorithm itself. We have to choose t somehow, and we'll talk about how that's done a little bit later. And finally, we measure in the standard basis. This gives us a candidate solution. There's no guarantee that it actually is a solution, but if we choose t well, the probability to get a solution can be made large. And here is the Grover operation itself. It's a composition of operations, all of them on n qubits, so this is an n-qubit operation. First, we have a ZF gate, or in other words, a phase query gate for the input function f, followed by a layer of Hadamard gates, and then we have Z-OR, which is the phase query gate for the OR function, and finally, we have another layer of Hadamard gates. So one iteration of step 2 can be implemented by a circuit having the form that's shown here on the slide. And here we have 7 qubits, but it could be any number of qubits in general. A key thing to note here is that we need one query to F to implement G. The query is needed to implement ZF. Well, none of the other operations have any dependence on F, so they don't require any queries. Therefore, this number t that represents the number of times we apply G in step 2 also represents the number of queries that we need. Here's a typical way that we might use Grover's algorithm, but not necessarily the only way. Like I said before, the first thing that we need to do is to choose t, and we'll get to that a little bit later. For whatever value of t we choose, we run Grover's algorithm for t steps, and then we measure to get a candidate solution x. There's no guarantee that x really is a solution, but we can spend one additional query to check. If we have a solution, then we can output it and stop. Otherwise, we can try again, possibly with a different choice of t, but not necessarily, or we can give up and report that there aren't any solutions. Like I said, that's not the only way that the algorithm can be used. For instance, Grover's algorithm often shows up as a subroutine inside of other quantum algorithms, but this is a natural way of applying it to the search problem. Next, we'll see what the Grover operation actually does to the state of the n qubits at axon. Let's think of our n qubits as forming a single register, and just to give it a name for the sake of convenience, we'll call it Q. Remember that what we do first in Grover's algorithm is to put Q into a uniform superposition of all n-bit strings, and we do that by simply applying Hadamard gates to n qubits in the L0 state. We then iterate the Grover operation G and measure. It's going to be helpful to partition the set of all n-bit strings into two sets, A0 and A1. A0 contains all of the strings that cause F to evaluate to 0, and A1 contains all of the strings that cause F to evaluate to 1. Another way to say that is that A1 contains all of the solutions to our search problem, while A0 contains all of the non-solutions. We're going to be especially interested in two quantum states. One is the uniform superposition over all of the non-solutions, that's ket A0, and the other one is uniform over all solutions, and that's ket A1. I should point out that these definitions really only make sense when these sets are non-empty, because otherwise we're dividing by 0. And as we go through this analysis of Grover's algorithm, we will be making that assumption. We can very easily figure out what Grover's algorithm does when f is either the constant 0 or the constant 1 function by treating them as special cases. But the end result is very simple. If every string is a solution, we will indeed obtain a solution when we measure, and if there aren't any solutions, then we won't obtain one because there aren't any. So hereafter, we're going to assume that both of these sets are non-empty, so that the definitions of both of these states make sense. The first step of Grover's algorithm is the initialization step, which puts Q into the uniform superposition over all n-bit strings. And just to give this state an easily recognizable name, I'm going to call it ket U, with U being short for uniform. It's important for the sake of the analysis that we first note that this uniform state, ket U, is contained in the subspace that's spanned by the two vectors ket A0 and ket A1. In particular, if we take the linear combination of these two vectors that's shown on the slide, we'll get ket U. Now the key to the entire analysis is the fact that the state of Q remains in this two-dimensional subspace no matter how many times we apply the Grover operation. So everything is going to boil down to what happens in a two-dimensional subspace. Now let's see what the Grover operation does, and in particular, what it does to vectors in the two-dimensional subspace spanned by ket A0 and ket A1. It's helpful to imagine that we split G into two parts. One part is the ZF gate, and the other part is the ZOR gate sandwiched between two layers of Hadamard gates. Here's the definition of ZF from before. And from that definition, it's pretty straightforward to see that its action on our two states, uniform superpositions of solutions and non-solutions, is simply to put a minus sign in front of ket A1, while nothing happens to ket A0. And that's all we really need to know about ZF for the sake of this analysis. For the second part, which is the ZOR gate sandwiched between two layers of Hadamard gates, let's start by recalling how ZOR is defined. One way to write it is as is shown here on the slide. This is the same expression as before. And another way to express it using Dirac notation is as we have here. And you can verify this expression just by thinking about how the operation on the right-hand side acts on standard basis states. In particular, it does nothing to the all zero state, and every other standard basis state gets a minus sign, which agrees with the definition of ZOR. So, if we sandwich this operation between two layers of Hadamard gates, then we get a similar expression, except that in place of the all zero standard basis state, we now have our uniform superposition U. That's because H tensor n transforms the all zero standard basis state to ket U, and also H tensor n is its own conjugate transpose, so it works in a similar way, acting from the right on the bra rather than on the ket. We're now going to figure out what G does to our two vectors, ket A0 and ket A1, using the facts that we just observed. Let's start with ket A0. Let's substitute the expression we obtained for the ZOR gate sandwiched between two layers of Hadamard gates. Next, we'll use the fact that ZF does nothing to ket A0, so we can get rid of the ZF operation. And now, using the description of ket U that we have at the top of the slide, along with the fact that ket A0 and ket A1 are orthogonal unit vectors, we can compute the action that we need to compute. And here's the result. Of course, if you really want to be convinced, you should perform these evaluations yourself at your own pace. Don't feel that you have to absorb this all in real time. At this point, we can evaluate what we get, and by substituting in our expression for ket U and simplifying, we get the final result that's shown here. In particular, notice that this vector is contained in the two-dimensional subspace spanned by ket A0 and ket A1, as I suggested before, and moreover, the coefficients happen to be real numbers. So let's clean this up so that we can remember the final result. And now we'll do something similar for the vector ket A1. We can use the same expression of G as before, and this time the ZF gate injects a minus sign, which here is reflected by the fact that we've swapped the two terms of the operation in parentheses. We then proceed in a very similar way. And the final result is similar, except that the two coefficients are swapped, and we now have a minus sign in front of one of them, and that's just how the algebra works out, and again, you can check this at your own pace. Notice that, once again, we have a real linear combination of our two vectors, ket A0 and ket A1. Let's clean this one up as well and put the end result together with the other one, and now we can see how G acts on the subspace spanned by our two vectors. One way to express this action is in terms of the 2x2 matrix M that's shown on the screen, and just to be clear, what we're doing here is to associate the first row and the first column with ket A0 and the second row and the second column with ket A1. We typically use matrices to describe the way operations work for standard basis states, but it is common to use matrices to describe the actions of linear maps on different sets of vectors, not just standard basis vectors, and here we're talking about what the operation G does just to the vectors ket A0 and ket A1. We can say more about what G does to vectors in the span of ket A0 and ket A1 if we take a closer look at this matrix M. And in particular, what we'll find is that M is a rotation matrix, meaning that its action on this two-dimensional space can be described as a rotation by some fixed angle. There are a couple of different ways to see that, and one is to observe that this matrix M can be expressed as the square of a matrix that looks somewhat simpler. That might be hard to spot if we're just looking at M by itself, but this isn't something that we need to discover on our own. We just need to verify that it's true, and we can do that by simply squaring the matrix on the right. Another way to write the matrix on the right, not including the square, is shown on this slide, and this is the typical way to describe a rotation by a given angle theta. The precise angle by which we're rotating happens to be the inverse sine of the square root of the number of solutions divided by n. And by the way, because this is the first time we're seeing it, let me point out that this angle is very important, and it's going to keep showing up as we continue with the analysis. The argument of the inverse sine function is a number between 0 and 1, and specifically the way that we're interpreting the inverse sine here is that it's the angle between 0 and pi over 2 that gives us the argument when we take the sine. So that's one way to think about this matrix that we squared to get M, and because squaring the matrix is the same thing as applying it twice, we see that M can alternatively be written as a rotation, not by an angle of theta, but by 2 times theta, because by squaring, we rotate by an angle theta twice. Now, returning to Grover's algorithm itself, after the initialization step, but before we perform any applications of G, the state of our n-qubit register Q is ket U, the uniform superposition over all n-bit strings, and here we have the same expression of ket U in terms of ket A0 and ket A1 as before. But now that we've identified this angle theta, we see that we could alternatively write ket U as cosine theta times ket A0 plus sine theta times ket A1. That's clear for the coefficient of ket A1, and for the other coefficient, we just need to observe that the size of A0 plus the size of A1 is n, and then we can get it using some basic trigonometry. So, that's the state we start with, and the first time we apply G, we rotate by an angle of 2 times theta, so the angle becomes 3 times theta in total. If we apply G again, the angle increases to 5 times theta, because we effectively rotated by an additional angle of 2 theta, and so on. So, after t applications of G, we can represent the state that we get as is shown on the slide, where the angle of our state is equal to 2t plus 1 times theta. That's 2 times theta for each application of G, along with an additional theta because that's the state that we started with. We can think about all of this in geometric terms. Here's the main idea. The Grover operation is a composition of the 2 parts we've already identified. One is ZF, and the other is Z-OR, sandwiched between layers of Hadamard gates. These operations are reflections, and when we compose 2 reflections, we obtain a rotation, which sheds some light on what we've already observed. So let's see how this works in detail. First, let's focus on ZF. We're going to restrict our attention to the same 2-dimensional subspace that we've been talking about, meaning the one that's spanned by ket A0 and ket A1. As we already observed, the action of ZF on this space is quite simple. It does nothing to ket A0, and it puts a minus sign in front of ket A1. This is a reflection, and specifically, it's a reflection about the line parallel to ket A0, which we'll call L1 just to give it a name. To see why it's a reflection, it helps to draw a picture. We have our 2 vectors, ket A0 and ket A1, which are orthogonal unit vectors, and we can think about the slide as consisting of real linear combinations of these 2 vectors. So the circle represents all of the unit vectors for which the coefficients of these 2 vectors are real numbers. Here's the line L1, which is parallel to ket A0, and if we consider some arbitrary vector psi on the unit circle, then the effect of applying ZF is to reflect about the line as is illustrated on the slide, simply because we do nothing to ket A0 and we put a minus sign in front of ket A1. So ZF is a reflection that can be visualized as we have here. The second part of G, which is Z-OR sandwiched between Hadamard gates, can be expressed as 2 times ket U bra U minus the identity matrix, as we've already seen. And again, this is a reflection, this time about the line L2 parallel to ket U, rather than ket A0. We can visualize this operation in a similar way to ZF. Here's the vector ket U, hypothetically, so this is the line L2 parallel to ket U. And once again, the action on an arbitrary vector psi is to reflect it about the line, which is L2 in this case. And finally, as I mentioned before, whenever we compose two reflections, we obtain a rotation. And specifically, it's a rotation by twice the angle between the lines of reflection. So let's draw a similar picture to what we had before. Here are the lines of reflection, which have the angle theta between them. And if we take some arbitrary vector psi, reflected about the first line L1, and then reflected about the second line L2, then the net effect of the two reflections will be to rotate the vector psi by an angle twice theta. And this is something that's true in general, and you can try it out on some examples for yourself to see that this is indeed the way that it works. Anyway, hopefully this helps to give you some intuition as to why the Grover operation has the effect of rotating vectors. Next, we'll turn to the issue of choosing the number of iterations t in Grover's algorithm. Let's start by thinking about how the analysis we've seen so far, which reveals what the Grover operation does when we apply it repeatedly to the uniform superposition, relates to the task we're hoping to solve, which is to find a solution to our search problem, or in other words, to find any string contained in the set A1. First, let's imagine that we have any state that's a linear combination of our two vectors ket A0 and ket A1. If we perform a standard basis measurement on the state, we're going to get an outcome in the set A1, which is the set of solutions to our search problem, with probability equal to the absolute value squared of whatever coefficient we have for ket A1. And for the vector shown on the screen, that coefficient is beta. This is intuitive. If we were to measure the state ket A0, we'd get a random non-solution, and if we measured ket A1, we'd get a random solution. So if we measure this state, we'll get a random non-solution with probability absolute value alpha squared, and a random solution with probability absolute value of beta squared. Now, we've already analyzed what happens when we run Grover's algorithm for t iterations. We get the state that's shown here on the slide. So, because the coefficient of ket A1 is the sine of 2t plus 1 times theta, where once again, theta is our very important angle that's determined by how many solutions there are, we'll see a solution with probability sine squared of 2t plus 1 times theta. We'd like to make that probability large, ideally as close to 1 as we can. So, as we're rotating the state vector by iterating g, we're thinking about ket A1 as the target, and we'll try to pick t so that we land as close to the state as we can. And as we're doing this, it's good to keep in mind that we'd also like to minimize t, because that's the number of queries we need. So if we want to make this probability close to 1 and minimize t, it makes sense to try to make the angle of our state vector close to pi over 2, because that's the smallest angle that makes the square of the sine large, so it's basically our first opportunity to make the probability large as we're rotating the state vector. Now we can't necessarily hit this angle pi over 2 exactly because t has to be an integer, but if we think about it approximately and solve for t as if it were an equality, then we see that ideally choosing t to be pi over 4 times theta minus 1/2 makes sense. But of course t must be a non-negative integer, so what we'll do is to take the closest integer to the value that we're shooting for, which is the floor of pi divided by 4 times theta. Taking the floor, by the way, just means that we throw away any fractional part. So in other words, it's the largest integer that's less than or equal to whatever we're taking the floor of. So going forward, we're going to be focusing on this specific choice of t. But there is another important consideration, which is that this specification of t depends on how many solutions there are, because the angle theta depends on how many solutions there are. Hereafter, I'm going to use the letter S to refer to the number of solutions, or in other words, the size of the set A1, just for the sake of convenience. The point is that our expression for t, the value that we're hypothesizing should be good, depends on theta, and theta depends on S, the size of A1. This isn't a problem if we know in advance how many solutions there are, but if we don't know how many solutions there are in advance, we don't know what theta is, so we can't pick t like this, and we'll have to do something different in that case. I'll come back to the situation in which we don't know S a little bit later, but to start, we're going to focus on the situation in which we do know how many solutions there are. We'll start with unique search, where there's guaranteed to be a single unique solution that we're looking for. I mentioned the unique search problem back in the beginning of the lecture. The input is a function f from n bits to 1 bit. There's a unique n-bit string that causes f to evaluate to 1, and the goal is to output that string. So this is equivalent to the unstructured search problem we've been talking about, but with the promise that there's exactly one solution. And in fact, this is the only version of the search problem that Love-Grover actually considered in his original 1996 paper that introduced this algorithm. For unique search, we have that S is equal to 1, and therefore this important angle theta is equal to the inverse sine of the square root of 1 over n. When n is large, this value is approximately the square root of 1 over n, and that's because for our smaller and smaller angles, the sine function starts to look more and more like the identity function. If we substitute that approximation for our selection for t, we see that t is approximately the floor of pi over 4 times the square root of n. And that's good because we see that, indeed, we're using big O of the square root of n queries. At this point, we've yet to take a look at exactly how well the algorithm performs, but we are on track to obtaining a quadratic advantage. Let's take a look at an example where capital N is 128, which is 2 to the power 7. So our function f is from 7 bits to 1 bit, and we're assuming that there's a unique solution. But to figure out how well the algorithm works, we really only need to concern ourselves with the angle theta, which we can calculate. It's approximately 0.0885 radians, which is a little bit more than 5 degrees. And if we plug that value into our expression for t, we get 8. So we're thinking about what happens when we search for a unique solution out of 128 possibilities using 8 queries. We can draw a picture to illustrate how the state changes over time as we perform iterations of the Grover operation. As before, we have the states ket A0 and ket A1, and in this particular case, meaning unique search, we have that ket A1 is in fact the standard basis state for the unique solution, whatever it happens to be, while ket A0 is the uniform superposition over every state besides the unique solution. Here's the uniform superposition over all strings, which we can write as cosine theta ket A0 plus sine theta ket A1. And it makes sense that ket A0 and ket U are close in this case because, as we've just observed a moment ago, ket A0 is almost the uniform superposition over all strings. There's only one string missing, and that's the unique solution. Applying G once causes a rotation of the state by an angle of 2 times theta. Applying G again rotates by an additional 2 theta, so this is where we are after 2 iterations. Here's 3, 4, 5, 6, 7, and 8. And now we see that we're pretty close to ket A1. So if we stop at this point and measure, we'll be quite likely to get the unique solution. And in fact, there's only about a 0.5% chance that we don't obtain the unique solution for this particular example. On the other hand, if we were to continue applying the Grover operation more than the recommended 8 times, the probability to get a solution would go back down, and over time it would oscillate as the state goes around the circle. So it is important that we stop the iterations at the right time if we want to succeed with high probability. Let's think about the probability that our choice for t reveals the unique solution more generally for different values of n. Let's write P of n1 to denote the probability that Grover's algorithm succeeds in finding a unique solution for each possible value of n. The 1 means one solution, and we'll extend this notation to other numbers of solutions shortly. Anyway, here's a table of these probabilities for small powers of 2. It starts with capital N is equal to 2, and the probability is 1/2, which isn't very good. But then for n equals 4, the probability is exactly 1, so it's actually perfect in this case. It's a good exercise, by the way, to explicitly go through how these two cases work, particularly the case that n is equal to 4. In that case, we're searching for one solution out of 4 possibilities. We need just a single query, and it works perfectly. As n gets larger, we do see some fluctuations. The probabilities go up and down a little bit, but they appear to be getting closer and closer to 1, and indeed that is true. It can be proved analytically that the probability is always at least 1 minus 1 over n. So that's good. The algorithm isn't perfect. We're not guaranteed to get a solution, but it is quite likely, particularly for large values of n, as well as the interesting anomaly that happens when n is equal to 4. I should also point out that we can always run the entire algorithm, including the measurement, as many times as we choose, and if any one of the runs succeeds, we'll get a solution. So if these probabilities aren't good enough for our needs, we can easily boost them just by running the algorithm again. So even if these probabilities were all equal to 1/2, for instance, we'd still have a pretty useful searching algorithm. Now let's consider what happens when there are multiple solutions. We'll start with a similar example to the previous one. Again, n is 128, but this time the number of solutions is 4 rather than 1. Again, we can calculate theta and t, and we get that theta is about 0.1777, or a bit more than 10 degrees, and t is 4 this time. So the angle is about twice the value from the previous example, and t is half of what it was. If we draw a picture like before, then here's where we start. Here's one iteration, 2, 3, and 4. In this case, we're very close to ket A1, and in fact the probability to get a solution this time is greater than 99.9%. But if we didn't know any better and we thought that there was only one solution, we would take t to be 8 like before, and we'd rotate almost all the way over to negative ket A0, and that would lead to a very small probability of success. So that's another example showing that there are good choices and bad choices for t, and here we see that a good choice when s is equal to 1 turns out to be a very bad choice when s is equal to 4. But assuming that we know s in advance, and we choose t according to our specification, then it turns out that Grover's algorithm will find a solution with probability at least 1 minus s over n, and often it will be much larger than that. It's also at least s over n, which is perhaps less interesting, but it's nevertheless relevant. Now, as I've already remarked several times, the number t represents not only the number of iterations of the Grover operation we perform, but also the number of queries we're making. So how does this number depend on s and n? First, let's start with the fact that the inverse sine of x is always at least x, provided that x is between 0 and 1, and that's pretty easy to show if you happen to know the Taylor series for the inverse sine function, but there are other ways to reason this, and we're just going to take that as given. That means that theta is at least the square root of s over n, and consequently t is at most pi over 4 times the square root of n over s. So that's actually even better than big O of root n. The larger s is in comparison to n, the fewer queries we need to make. As we've just seen, Grover's algorithm works quite well when we know in advance how many solutions there are. But what do we do if we don't know how many solutions there are? Well, there's one very simple approach, and that is to just choose the number of iterations randomly. Specifically, choosing t uniformly at random between 1 and the floor of pi over 4 times root n turns out to be a pretty good way to do this. The upper end of this range is approximately the number of queries we need for unique search, which is when the angle theta is as small as it can possibly be, excluding the trivial case where there aren't any solutions. The idea here is that instead of carefully aiming our state vector at ket A1, like we did when we knew how many solutions there were, we'll rotate by a random angle, as if we're giving the state vector a haphazard spin. If there happens to be just one solution, then our random spin could push the state vector close to ket A1, but it might also just go part of the way there. And if there happen to be multiple solutions, then our random spin could potentially send the state vector around the circle multiple times. So we don't expect this to reveal a solution with a probability close to 1, but the chance that this leads to a solution, if there is one, turns out to be pretty good. It's always at least 40% in fact. And remember that we can always boost the probability of finding a solution by repeating the process, choosing t independently each time. By doing this, the chances of not finding a solution when there is one decreases exponentially in the number of times we repeat. So, if we want, say, a 99% chance to find a solution, we could run this simple procedure 10 times. Naturally, if we don't find a solution, we'll output no solutions. And if there aren't any solutions, we won't find any solutions. So in that case, we always output the correct answer, which is no solutions. If there are solutions, we might fail to find one and incorrectly declare that there are no solutions, but the probability of that happening can be made very, very small. We also have, as I mentioned a few moments ago, that this requires a number of queries, or evaluations of f, that's big O of root n. So, using Grover's algorithm, we can still solve the search problem with high probability with big O of root n queries, even if we don't know how many solutions there are. There's also a more sophisticated approach that can lead to a reduction in the number of queries required as the number of solutions grows. I won't describe it in detail. Instead, I'll just focus on the main idea. We start with capital T being equal to 1. We then run Grover's algorithm for a random number of iterations where the upper bound is t. So the first time we get to step 2, we're going to run Grover's algorithm for one iteration, but t is going to be increasing. If we find a solution, then we output that solution and we stop. And if we don't find a solution, what we'll do is to make t larger and then try again. And at some point before t gets too large, we'll terminate this process and declare that there aren't any solutions. It's the same basic idea that we have in the simple approach where we're giving the state vector a random spin effectively, but here we're starting out with lighter spins first, where t is very small, just in case there are a lot of solutions, and this way we won't waste queries by making the state go around and around the circle by spinning too hard. But if it doesn't work, meaning that we don't find a solution, we'll try again, and we'll just make the spin a little bit harder. The rate of increase of t has to be chosen carefully, but one way that it works is to replace t by the ceiling of 5/4 times t. So t is being increased exponentially, and we can think of it as spinning 25% harder each time. And it's important for the analysis that t does increase exponentially like this. Why 5/4, you may ask? Well, it's just a number that works. There's actually a range of values that work, but 2 doesn't work, for instance. Doubling t each time is too fast of an increase to take full advantage of the benefits of lighter spins. Anyway, the point of this more sophisticated method is that it gives the same asymptotic bound on the number of queries we require as before, big O of root n over s. But we don't need to know in advance how many solutions there are. We can stop when t gets to root n, so if there aren't any solutions, we'll conclude after big O of root n queries that there aren't any solutions. And that's how we can choose the number of iterations in Grover's algorithm. To conclude, I'll make just a few brief remarks about Grover's algorithm. First, within the query model, Grover's algorithm is asymptotically optimal. What that means is that it's not possible to come up with a query algorithm for solving the search problem, or even the unique search problem specifically, that uses asymptotically less than big O of root n queries in the worst case. That's something that can be proved rigorously, keeping in mind that we're talking specifically about the query model, in which it's possible to prove such things, and there are in fact multiple known proofs. Quite interestingly, this was known even before Grover's algorithm was discovered. Grover's algorithm matched the already known lower bound on the number of queries required for search. Second, Grover's algorithm is quite broadly applicable, in the sense that the square root speedup that it offers for the unstructured search problem can be obtained in a variety of different settings. For example, sometimes it's possible to use Grover's algorithm on top of another algorithm to get a quadratic improvement beyond the performance of that algorithm. Grover's algorithm is also quite commonly used as a subroutine inside of other quantum algorithms. As just one example, we can use Grover's algorithm to get a quadratic advantage over classical algorithms for the minimum problem that I mentioned at the start of the lecture. And finally, the technique used in Grover's algorithm, where two reflections are composed and iterated to rotate a quantum state vector, can be generalized in a pretty major way. So, it may be true that Grover's algorithm isn't likely to lead to a practical quantum advantage anytime soon, if ever, but Grover's algorithm is, without a doubt, a fundamentally important and broadly applicable quantum algorithm, and it's representative of a more general technique that has many uses. And that is the end of this talk, which has been about Deutsch's algorithm and Grover's algorithm. In part 2, which is the next lecture coming up, I'll discuss the phase estimation problem and Shor's algorithm, which extend some of the ideas that I have described in this lecture to solve computational problems that we don't know how to solve efficiently with a classical computer, in particular, the integer factorization problem. I hope you'll join me for that one. Goodbye until then.